Take it away, Greg.
Thanks, Grace. All right, yeah, so you guys get to hear me rant about atmospheric rivers for a bit less than an hour. Let's see, yeah, so thanks for the introduction, Grace. And yeah, I also wanted to acknowledge that this is kind of an evolving talk that started with one that Doug put together some years ago. And then it's kind of just been iterated and iterated over the years and kind of putting in new stuff, taking out old stuff. So, all right, so first off, what is an atmospheric river and why should we care about them? So these are long, narrow bands of moisture transport in the atmosphere. They're responsible for about 90% of the equator to pole water vapor transport. And they're also responsible for about 30 to 50% of Western North America precipitation, which makes them critical to water supply in many regions, and obviously, especially in more towards the Southwest US, water supply is a very important topic. But at the same time, they are also responsible for basically the biggest floods that we've seen on the West Coast, billion-dollar-plus disasters. So just basic coastal geography for people that maybe just moved here. So basically the whole west coast of BC is lined with mountains. That's the Coast Range. We also have the Vancouver Island Range, and we also have Olympic Mountains down here in Washington State. And this will be important when we talk about the orographic precipitation component of atmospheric rivers. So just to motivate the talk a bit, I'll talk about two cases here briefly. So one was back in October 2003. This was the heaviest BC rainfall in recorded history. Actually, so this is, you're looking at a water vapor imagery, which, as I'll talk about later, is not really actually the best tool for diagnosing water vapor, but nonetheless, you can see this system with, and this satellite imagery is showing water vapor in the upper atmosphere associated with this system coming into the BC South Coast. So this is Daisy Lake Dam. This is the Sea to Sky Highway here on the left side. So you drive by this dam if you're driving up to Whistler. This is what it looks like on a normal day. And then this is what it looked like during this atmospheric river event back in 2003, spilling lots of water out of the spill gates there. Farther up the Sea to Sky Highway, this is a bit north of Whistler, Rutherford Creek. So again, this is the Sea to Sky Highway, completely washed out, and the railroad as well there. So these are some rainfall totals from the event, 5-day totals. So some really astounding totals here. 455 millimeters, which is about 18 inches in Squamish over the period, which pretty well obliterated the previous record. And then, lots of other totals in the 200 to 300 millimeter range. And then it's estimated that in the Illaho Valley, which is a bit west of the Sea to Sky Highway, up to 600 millimeters fell over a 4-day period. So really unprecedented, outstanding precipitation totals from that. And then this is one that people may be more familiar with. Last year, from the 13th to 15th November, we had an atmospheric river, and this is the costliest weather event in BC history. The insured losses are about $500 million, but that doesn't include uninsured losses and infrastructure damage. And so the total loss estimates are somewhere between $2 and $7 billion. So very, very costly disaster. And there was numerous landslides with this system. This is Highway 1, I believe, going up the Fraser Canyon. Road completely washed out there. This is on Highway 99 north, basically between Whistler and Lillooet. They had a couple landslides there as well. And I'm not sure which road. This might be Highway 7, I'm not sure, but there was 2 landslides that basically stranded people on that highway. They were sandwiched between the landslides, and so they had helicopter evacuations there. So basically all the roads connecting Vancouver to the rest of Canada were taken out by this storm. And then in addition to that, we saw large-scale flooding of farmlands in the Abbotsford area, and Highway 1 was also underwater in that area. So quite a major disaster for the South Coast here. If we look at rainfall totals, you can see they're not quite as impressive as the 2003 event, but still very impressive nonetheless. Over 200 millimeters at many of our precipitation gauges in the mountains of the South Coast, and then in the Eastern Fraser Valley, also some, that's where we saw some of the highest precip totals, about 270 millimeters at Wallach, which is a reservoir in the Eastern Fraser Valley, and at Hope in the Eastern Fraser Valley. So this wasn't the wettest event on record, but it certainly ranked up there, and certainly the impacts were, like I said, the worst we've seen. Okay, so that's some pretty good motivation for understanding more about atmospheric rivers. So we'll talk about a bit more now about what they are. So they're a relatively narrow band of water vapor transport, generally 400 to 600 kilometers wide, over 2,000 kilometers long. And the way we look at them is using these fields called integrated precipitable water. That's IPW, integrated precipitable water, or also known as integrated water vapor, IVW. And we look at this in a column in the atmosphere, which I'll talk about in a second. And then another quantity that we use is integrated vapor transport. So first, to talk about integrated precipitable water, it's the depth of water in a column of the atmosphere if you were to precipitate or condense all the water out of that column as rain, and it's measured as a depth in millimeters. There's a little XKCD cartoon showing this. So you have the clouds, water vapor, and rain all in a column. If you just basically condense all that out to the bottom of the column, that's the total precipitable water. For an atmospheric river, the general threshold for West Coast North America atmospheric rivers is greater than 20 millimeters, but greater than 30 millimeters for strong atmospheric rivers. And as I said before, you're looking at lengths greater than 2,000 kilometers and widths less than 1,000 kilometers. So that's used in conjunction with the winds throughout the atmosphere, and you can use both of those things to compute the integrated vapor transport. And so this is the advection of integrated precipitable water by the wind. It's measured in a hard to say unit, kilograms per meters per second. So I'll just say units, I think, instead of saying all that. So for an atmospheric river, we're looking at IVT of greater than 250 units. It's the standard definition, but it really does kind of depend on where you are on Earth, and even kind of what climate you're in, which is one of the things. So I guess I should also mention I've been virtually attending the International Atmospheric River Conference this week, and something that people were discussing today is, do we change some of these thresholds as we go forward in the with climate change? Excuse me. Because you're going to see greater water vapor content in the atmosphere, it'll be a lot easier to exceed these thresholds for different strengths of ARs, and should those change, or how should we deal with that? Anyway, in the current climate for our coast here, strong ARs, we're usually looking at 850 units or more. This is the equation, which I'm not going to go through, but it's just, yeah, the definition is at the top of the slide here. And then just a bit more of a note on atmospheric river detection and tracking. The community uses the abbreviation ARDTs for atmospheric river detection and tracking algorithms. So they used to be simpler, but now as the science has evolved more, they've gotten more complex. So this is an example of a fairly popular one by Guan and Wasseler. So these are automated algorithms that they run on atmospheric science or atmospheric reanalysis data sets to identify and track atmospheric rivers, both in historical reanalysis data sets and also going forward in climate models. So one example would be a length greater than 2,000 kilometers, a length to width ratio of more than 2. And they have a season dependent 85th percentile of vapor transport but no matter what the season, it has to be at least 100 units and greater than 50 units in the poleward direction. And then they also have a direction coherence metric. So more than half of the area of integrated vapor transport direction has to be within 45 degrees of the mean. So it can't be too meandering. It has to be kind of more or less directed in a similar direction. So that's an example of one type of detection algorithm definition. And another thing that people talked about a lot this week is that if you're doing an AR study, you want to try out using several different AR DTs because your results might vary quite a bit depending on which algorithm you use. All right. So although we use integrated precipitable water and integrated vapor transport to diagnose and identify atmospheric rivers, they're not the whole story as far as the impacts. So yeah, it used to be that people used IPW. Now people use a lot IVT a lot more. That's the kind of standard these days. But to actually get precipitation out of these atmospheric rivers, you don't just, the vapor transport is not enough. You also need to lift that moisture. And typically, going back to that Geography 101 slide, that lift is produced primarily by horizontal flow across the mountain barrier being the coast mountains in our case. But even then, that's still not the whole story. You might have other considerations like atmospheric stability, the angle of incidence at the coast. So if you have an atmospheric river that's hitting the mountains at fairly perpendicular direction, you're going to get more rain out of it than if it's intersecting the mountains at an acute angle. So I do think IVT is a very important tool for looking at atmospheric rivers, but I think we should be hesitant to really focus on the IVT itself, and I think it might be more useful to focus on the actual precipitation that we're expecting out of it as predicted by the models. So now we'll look a bit at the 3D structure of atmospheric rivers. This is a diagram that I was introduced to this week. So this shows a low pressure system. So the low pressure center would be right about here. And then this is the warm front and then the cold front coming out of the low pressure system. And the light blue shading here is where an atmospheric river would typically be located. So just ahead, along and ahead of the cold front. So this paper looked at airflows, and it was kind of a unique paper because it looked at storm relative airflows and not Earth relative airflows. So it was an interesting way of looking at it. But anyway, they found that this feeder airstream out ahead of it played an important role in feeding moisture into the atmospheric river. I've also seen other studies that argue that even this dry intrusion behind the cold front is fairly important because since the air is colder and drier, you get even more moisture flux off the ocean compared to other areas. And then there is some ambiguity of how an atmospheric river is different from the warm conveyor belt. And essentially the atmospheric river and warm conveyor belt are maybe have some overlap, but then the warm conveyor belt ascends up over the warm front, whereas the atmospheric river is really confined to the lower levels of the atmosphere. And that's shown in this cross section here, where the orange shading shows the moisture, the water vapor flux basically into the page. And the lines here are the cold front. So you can see that the atmospheric river is just out ahead of the cold front with most of the moisture advection at the lowest levels. So how do we detect and diagnose atmospheric rivers? First, I'll do a mini rant on the misuse of water vapor satellite imagery. Sometimes people try to use water vapor imagery to actually look at the water vapor content of the atmosphere, but that's really not what it is or what it's for. So water vapor satellite imagery does not measure water vapor directly. It infers it from infrared radiation that's absorbed and emitted by the water vapor, and so it only gives you an indication of water vapor in the upper troposphere, because that's as far as kind of that's where it's getting the infrared from, is just from the tops of the clouds. And it can't infer water vapor in the lower troposphere, which is where it matters. As we saw before, most of the water vapor transport happens at the very lowest levels. So this is an example on the left side here. This is water vapor imagery showing water vapor in the upper troposphere over the Southwest US, but basically nothing down here over the Caribbean. And in model world here, you can see that basically the strongest water vapor transport in this region is occurring over the Caribbean, where it's just showing dry air at the upper levels. So water vapor satellite imagery is useful for looking at upper level horizontal airflow, large scale patterns in fluid motion, even small scale features that might not be picked up by the models. And you can get some indication of upper level subsidence and descent. Okay, so what types of satellite imagery are useful for looking at these? So this is passive microwave detection imagery. And in this particular product, the integrated precipitable water that's detected by the passive microwave sensor is then advected using model winds to create this animation. So this is a pretty nice way of looking at how the water vapor is kind of flowing and evolving over time in the atmosphere. We can also calculate integrated vapor transport and integrated precipitable water on the model grids and then visualize them. So this one is one that the WFRT produces, and in the shading there, it's IPW, and then the vectors indicate IVT. So you can see here, sometimes they talk about the IPW reservoir in the tropics, so that's where we have lots of really warm, moist air. And then occasionally you get these atmospheric rivers that kind of pick it up and bring it northward. And in this particular product, the white and purple arrows are showing the strongest IVT. So then there's the Center for Western Weather and Water Extremes, CW3E. Neither of those things are easy to say, but they have various tools for looking at atmospheric rivers. They have a pretty large center down there, very well funded, and they've really pushed the field forward a lot in terms of our knowledge of atmospheric rivers and prediction of them. So these are examples of some of the tools that they have. So this one is showing instantaneous IVT from the ECMWF model. And then perhaps even better than that is time integrated IVT. So this shows 72-hour time integrated, so it's both time integrated over 3 days and then vertically integrated through the atmosphere. And this is important because one of the characteristics that can make atmospheric rivers particularly devastating is that they tend to hang out, or not tend to, but they can sometimes hang out over a certain region for an extended period of time. And so if you're looking at kind of an extended, a multi-day period of high integrated vapor transport, then that's what is going to cause really big flooding issues. Here's another tool from them. And this shows basically so this is latitude on the y-axis and then forecast time on the x-axis. So it shows expected integrated vapor transport through time at different latitudes and the probability of having an atmospheric river. So yeah, basically showing the probability of having an atmospheric river at a given latitude and forecast time. And then this plot also shows kind of the probability of seeing an atmospheric river at a given latitude. And then this is a tool, I believe it was new last year from them. So you can select what latitude along the coast you want to look at. And so this is not too exciting because we're in an unprecedented drought, but there is a bit of IVT happening up on the north coast. And so you can select the latitude there, and then it will give you a forecast meteogram forward in time for that point, and then identify areas, or sorry, time periods where you're getting, where you're above that atmospheric river level of IVT. So these blue shading here are indicating periods of time where you're getting greater than 250, or actually I believe it's maybe greater than 500 units of IVT. And then you can also see an ensemble spread here and things like that. And then it even plots them up on this atmospheric river scale over here. So this is, the first episode is A, and you can't really see it here, but it's underneath this B. So it shows where that particular event falls on the atmospheric river scale. And I'll talk about the AR scale here shortly, I think maybe on the next slide. Yeah. So the folks down there, Marty Ralph leads the center, and he's kind of the biggest name in atmospheric rivers. And he and others came up with an atmospheric river scale because their logic was these are basically the biggest weather impacts, the biggest type of weather events that impact the West Coast. So we should have a scale kind of akin to the hurricane scale. So the scale has pluses and minuses. On the plus side, it's simple. It's very easy to communicate, and it's similar to the hurricane scale, which people have some familiarity with. The downside, as is the case with the hurricane scale, is that the category does not equal the impacts. There's, obviously some correlation, but there's not a perfect correlation. And we saw this with Ian in Florida just a short while ago. It was a Category 4 storm, but Category 4 storms come in many different flavors and sizes. They vary in size, duration. Their kind of local interaction with the coastline can determine storm surge. So although there's some utility to having these categories, they can be misleading. And I do personally feel that we'd be better off just communicating the impacts. So just skip right to the part, talk about how much precipitation, which areas are going to get, how much storm surge different areas are going to get, how many, what are they going to get in terms of winds. And I kind of feel the same thing about this atmospheric river scale. I think it can be useful for kind of categorizing and getting like a rough feel for these storms, but when it comes to communicating to the public, I think we're probably better off just actually telling the public what kind of precipitation and flooding to expect out of these events, because a given Cat 3 or Cat 4 atmospheric river is gonna have different impacts. Yeah, as I mentioned before, the atmospheric river's orientation with respect to topography, if it's coming in at a more perpendicular angle versus acute angle to the topography, it's going to have varying levels of resulting rain. There's also this concept of wet versus windy ARs, and basically the two terms that make up the IVT calculation are the wind and the integrated vapor. And so you can imagine that for a given IVT value, you can either get to that IVT value by having kind of relatively stronger winds and lower integrated vapor transport, or sorry, integrated water vapor, or the opposite, where you might have slightly weaker winds, but then you have higher water vapor values that kind of give you that same IVT value. And those will give you different amounts of precip. We've found here BC. Typically the early season atmospheric rivers, type that we're, I guess, not going to get this year. Since the atmosphere is warmer, they tend to have more water vapor and weaker winds with them, and so you tend to get less precipitation for kind of a given amount of IVT. Whereas kind of in late November, you might have a somewhat cooler system with stronger winds, and you might get relatively more precipitation for the same IVT. All right, so and then to talk a bit about, you might hear some of these terms a bit. Tropical punch is kind of a, I guess, colloquial term that is usually used to refer to a stronger or more severe atmospheric river that has kind of more of a direct feed from the tropical latitudes. Pineapple Express would be kind of just another term for atmospheric river, maybe more of a moderate strength one. And then you have weak ARs at kind of lower end of the scale. And so this is the scale here. And so, it takes into account IVT, but then also the duration of the event. And this is, basically the maximum IVT that you get at any point during the event, and then the total duration of time that you're above this 250 unit value. And so depending on that, for longer duration storms, how do I best phrase this? If you have a storm that has a maximum IVT of say 800, but then it's persisting for more than a day or more than 2 days, then that kind of bumps it up in AR category. It can go from a Cat 2 to a Cat 4 if it persists for a longer amount of time. Okay, so we'll go back to kind of what these look like at different levels of the atmosphere. So this first map here is, we're starting at the near the top of the tropopause or troposphere. Jet level winds. So this is showing jet level wind speeds and 25 kilopascal geopotential heights. And so this is roughly kind of the jet maximum through here. And you might expect an atmosphere, kind of the low level water vapor transport to be maximized along a line like this. So at the upper levels here, one setup for atmospheric rivers is basically a trough with a lot of north-south extent. And so with that, you're able to advect air out of the subtropics and bring it up into the mid-latitudes. Another potential setup, this is a map looking at 50 kilopascal geopotential heights, somewhere in the middle of the atmosphere. You can have multiple upper level troughs that are superimposed in just the right way so that you still get that kind of continuous feed of moisture from the subtropical latitudes up into the more mid-latitude area. And then this is just overlaying those same lines with the IVT plot here. So you can see what that looks like at the low levels. Yeah, and the other thing that I've been, saying, advected from the subtropics and tropics, and there's an asterisk on that because that's a bit complicated, and I'll talk about that a bit more later. And then just another plot of low levels. There's a lot going on in this plot. I apologize for that. This is looking at the 85 kilopascal level, so kind of lower atmosphere. The solid lines are temperature. And so you can see that there's fairly tightly packed temperature lines here, which indicate that the atmospheric river is more or less coincident with front. And then also in the green shading is relative humidity. So that's, again, as you'd expect, to have fairly saturated air, coincident with the atmospheric river as well. And then just the wind barb showing southwesterly flow kind of along the atmospheric river. And then the result of all that is large amounts of precipitation. This particular event was forecast to have 5-day totals in excess of 300 millimeters along the higher terrain of the Central Coast. Okay, next we'll talk about what makes atmospheric rivers different from other fronts. So I think the main differentiator is that you have this kind of extended feed from the subtropics or tropics. And as a result of that, you have a relatively warmer air mass, and what comes with that is that the air mass has a higher capacity for moisture. One thing to think about in the context of climate change is that we saw I don't know how many years ago now, the blob, which was this warm anomaly of sea surface temperatures off the coast. But even without the blob, just in the context of climate change, as warmer sea surface temperatures make their way northward, having that feed from the subtropics becomes a bit less important, since you can get kind of maybe similar sea surface temperatures as up into the mid latitudes. And we do occasionally see these types of events. This event back in 2015, where there's a westerly atmospheric river event. And then that gets kind of into, do you still call it an atmospheric river or not? If it's just westerly, if it doesn't have kind of a poleward water vapor transport component to it, and that's up for debate. Other differentiators, strong winds, and again, kind of in a elongated area of continuous strong winds. And with stronger winds, you get stronger moisture flux across the mountain barrier, more lift and more rain precipitating out. And another thing that you sometimes see with these events, I talked about how longer duration events, are more prone to be associated with flooding because it's raining for a longer time. It's pretty simple. And what we see with these types of events often is that we talked about how atmospheric rivers are kind of along and just ahead of a frontal zone. And so what sometimes happens with these events is you have multiple low pressure waves along that frontal zone. And so that causes, you can see that in the animation here, it causes the atmospheric river to kind of waver back and forth over, maybe a period of a few days over a certain area. So it just keeps getting hit. It's kind of like, being hit with a hose or something like that. And then, the results from multi-day situation like that result in heavy multi-day totals. Okay, next I'll talk about climatology of ARs. So up in our neck of the woods and Pacific Northwest US, they are most frequent in the month of November. And then kind of as the jet stream migrates farther south, as you get more into the heart of winter, so do the frequency of atmospheric rivers. So in North and Central California, they're most likely to get them in December. And then as we get into Southern California, they're most likely to see them in January. This plot shows the percentage of annual precipitation that's attributable to atmospheric rivers. So along the west coast of the US, much of the west coast of the US, you can see that most of the annual precipitation is associated with atmospheric river events. And then as you get farther inland, the percentages generally decrease. And then the plot on the right here is similar, but it's the percentage of snowfall that's attributable to ARs. And so the Cascades of Washington and Oregon really stand out here. About half of their half of their snowfall is associated with ARs. And then as you move inland, the fractions decrease, but it's still, a third or so of their snowfall is associated with atmospheric rivers. So it's still definitely a very significant portion, and similar for the Sierra Nevada. And then as far as frequency globally, so this is, atmospheric rivers are not just a thing that happens to the west coast of North America. They definitely happen globally. In the conference this week, it's based in Chile. So there's been a lot of talks of atmospheric rivers impacting Chile, but then also Antarctic ARs is a pretty hot topic. And again, these types of maps are very susceptible to the type of AR detection algorithm you use. And the way this algorithm was designed, it's not really going to pick up on these polar ARs. So that's why there's no ARs indicated over Antarctica or over the Arctic either, even though there are ARs that affect those regions. But anyway, you can see the general moisture transport from the western subtropical Pacific into the northeast Pacific where we are. And you have a similar frequency of AR tracks kind of following the Gulf Stream into Northern Europe. And then, yeah, and then in Southern Hemisphere, you also have quite a high frequency of atmospheric river events. Here's some examples of non-West Coast ARs. The ARs that originate over the Gulf of Mexico impact the Appalachians is something that that people are currently studying. I think some of the people at the Center for Western Weather and Water Extremes are studying that currently. And then this is an example of an atmospheric river impacting the UK. Okay, so now we'll talk about whether or not it is a river, whether that metaphor is appropriate. And the answer is sort of. So the typical lifetime of water vapor in the atmosphere is about 1 to 10 days, but it is shorter within frontal zones. And as we've talked about, the atmospheric rivers are basically within or right adjacent to frontal zones. So water vapor cycles through frontal zones and atmospheric rivers, in particular at low levels. So it's not just a direct transport where water gets picked up from the subtropics or tropics and then gets deposited in the mountains of BC. And there is a mixture. Some moisture travels far and some does not. Yeah, so it's important to keep in mind that a lot of these maps we use, like the IVT maps, are just a snapshot, and that the wind fields do evolve with time. So this is some studies that have tried to look at where the water vapor is coming from. So this is one from a talk this week that is showing that about 80% of the precip in this event was, they used, I guess, water vapor tracing in the WRF model, and found that about 80% of the precip with this event was from the subtropics. So that the actual water vapor was from the subtropics. And I think elsewhere in this paper, they found a bit more of a mixture where definitely the upper atmosphere was dominated by moisture that was from the directly from the subtropics, whereas the lower atmosphere was more of a mixture where you saw water vapor cycling through as it was transported up. This study looked at atmospheric rivers that made landfall in Norway, and you can see from atmospheric river events, they had a higher percentage of water vapor that originated from this T2 region down at 30 to 40 degrees north, whereas other types of low pressure systems had far less long range water vapor transport. And then lastly, I'll talk about predictability. So I often get the question like, oh, how far out can you predict the weather? Can you predict the precipitation event? And it's not an easy answer. You can't just say like 6 days. The answer is basically that you have a very kind of wide range of uncertainty, and then as you get closer, that uncertainty narrows more and more. So at 5 to 12 days is when you typically get some sort of useful information about atmospheric rivers. So you can, the large scale pattern is typically pretty forecastable at these forecast horizons. And so it might be the case that next week the models have this large scale pattern that's just not possible to get an atmospheric river out of. Maybe we just have kind of a ridge upstream. We just have northerly flow over BC, and then we know we're not going to get an atmospheric river next week, even if there's some variation in that forecast. So to look at forecasting at these timescales, it's really important to use ensembles. So one thing you might use to get an idea of the upper level pattern, large scale pattern, is ensemble 500 or 50 kilopascal maps, which is an example of that is here, where you can see the heights, and then the colors show the spread in the ensemble, how much uncertainty there is in the pattern. There's also ensemble IVT maps that you can look at. And then you can also look at things like ensemble meteograms that might show the spread of forecasted precipitation range. And in particular, for potential high impact events, you want to look at, is the ensemble producing any outliers, any really high outliers that might suggest that, okay, a high impact event is within the realm of possibility for this period. At 4 to 7 days, you start to get, you can start to get some idea about slightly smaller scale features like frontal zones. And so at this type of forecast horizon, you'd be trying to narrow down kind of the extent and strength of the atmospheric river and the region where it might make landfall. So for example, if we're looking at this precipitation map here, you can see pretty clearly that this model is favoring Northern California. You can still look at also ensemble precipitation plots for timescales like this as well. But this 4 to 7 day range, you don't want to be trying to pinpoint which basin it's going to hit hardest, or exactly how much precip is going to happen in a given basin, because there's still some uncertainty in exactly where that's going to make landfall. And then at 0 to 3 days is when you start to really try to narrow things down to the extent that you can. And this is to some extent how much you'll be able to narrow it down is kind of how do I say this? I guess it has some to do with how good of agreement the forecast models. If there's still a lot of spread, then they're telling you that there's still a lot of kind of uncertainty and possibilities of where the atmospheric river might end up. Whereas if they're in their pretty good agreement with the location of landfall, then that might give the forecaster more confidence of the atmospheric river's location. So you start to look at more deterministic output at these timescales. There was a study that showed that at 1 to 3 days, there's 100 to 600 kilometer location error. So there is still some location error, and so at these types of timescales, you can probably say, oh, it's going to hit the South Coast, but which part of the South Coast is going to hit the hardest? That's harder to say. Another point to make is this gradient issue. So this red outline here is one of our watersheds, and then the shading here is precipitation amount. And you can see that there's this really steep precipitation gradient across the watershed. And so any slight shift in the location of that precipitation maximum is going to drastically affect how much precipitation you get in that watershed. So that's another thing to watch out for. And then once you get to kind of within several hours of the event, that's when you're going to be looking at also using satellite and radar to try to figure out when the event might start and when it might end. So one example of I don't know, partial success, partial failure with predictability of atmospheric rivers was last November's event. We worked with Dominique on the weather forecast research team to, basically she built this ensemble forecast system for us. And we tried to engineer it so that it would have a lot of dispersion to try to better capture kind of the possible extreme ends of the forecast distribution. And there's 167 models that go into it, so it's quite a large ensemble. And so this is what the forecast looked like for this last November's event. You can see at a lot of basins across the South Coast, the forecast did quite well for the first part of the event. So the blue here is the observed, and the red is the ensemble mean, the most likely forecast. And so you can see they were in quite good agreement for the first part of the event. And then in the second part of the event, the observed precipitation rates really skyrocketed. And so at most locations across the South Coast, the observations verified near the top of the ensemble envelope. And then in the Eastern Fraser Valley at Wall H here, the observations actually verified well outside the ensemble envelope. So, it was a forecast success in that we were able to tell end users several days in advance that there was going to be a heavy precipitation event coming, high impact event, but the totals were quite a bit off our most likely scenario, and even above our highest scenario in some cases. So there's still work to be done in this. We did adjust the composition of our ensemble after this event to try to better handle high impact events like this. And then kind of future plans are to develop more of a high resolution convective allowing ensemble. And that would better resolve topography, any topographically induced mesoscale features, and also small scale, heavy to extreme precipitation rates, which the lower resolution models are just not capable of resolving. Okay, so the takeaway points. Number one, atmospheric rivers are a primary source of water vapor transport, precipitation, and flooding events for Western North America. Integrated vapor transport is the best way to identify them and their strength. Heavy precipitation rates result from large moisture flux as this moisture is lifted and then rains out of the atmosphere over a mountain barrier. And if you have multiple waves along the atmospheric river, that can cause the event to persist over a given area for an extended period of time. And as far as predictability, you can get a pretty good idea of what's going to happen and what region will be impacted a few to several days in advance, but pinpointing the exact area can be tough, as we saw with last November's event. And that's all I have. Take any questions.
Oh, gee, Greg, it's Ian here. I'll have a crack. That was fantastic, by the way. I really enjoyed that. And you kind of hit on some things that I've kind of been struggling with a little bit. And it's more about semantics. And last year in particular, I had the impression that when you listen to weather forecasts and so on to the public, and the public may well be feeling the same way, that essentially anything in the popular imagination now that has any significant rain with it tends to be called an atmospheric river. And it was interesting to see, and I hadn't seen before, that categorization of atmospheric rivers, and there was one at the very bottom which said, essentially beneficial, something that we'd like right now with some rain and so on. And really, I don't know what my question is. It's kind of asking you, do you have your sense, and again from the conference, that people are struggling somewhat with how to define what an atmospheric river is, and are a little concerned that it is being used to explain just about everything where there's a significant amount of rain? Do you understand what I mean?
Yeah, and I think that's something that we even struggle with somewhat here at BC Hydro. Yeah, I mean, we'll often debate like, oh, should we call this an atmospheric river? Should we not? Because atmospheric river certainly has a certain connotation with it, and it kind of raises some alarm bells here at BC Hydro, where people are like, oh, geez, yeah, that means a lot of rain, and there can be, atmospheric rivers that are lower impact, that might just have kind of moderate to heavy precipitation event or totals associated with them. Yeah, I do. My general sense is that people are perhaps a bit too trigger happy with the atmospheric river term, and I know that on camera meteorologists are typically pretty pressured from their producers to try to make it more sensational, and so that might be contributing to that. Yeah, and I can imagine. I don't really watch TV weather people, but I can imagine them kind of taking the AR scale and running, because that's like, oh, we have something like a hurricane scale. That's pretty exciting, and so it would be, I don't know, kind of unfortunate. And as I said, I mean, I guess it makes for good television, but I think as far as communicating the hazards and impacts, it's better to just say we're going to get this much rain and we're expecting this much flooding, and it doesn't matter what the category is associated with that.
Yeah, I agree with you actually, Greg. I think that's exactly right. Thanks, that was really helpful.
So I have a question. Greg, you showed a lot of tools from the CW3E, whatever it is.
Yeah,
Are those
C3PO,
tools,
yeah.
are those tools publicly available?
Yeah. They're on that website. Let's see if we go way back. Yeah, they're on this website here. Yeah,
Okay.
if people can message me and I can give them the link too.
Oh, that's great. At least can start doing our homework and making our own forecasts using these products.
Yeah. One thing, or one tip for this anyway, if at least wants extra forecast skill, is a lot of the products, it defaults to using the GFS or GEFS, which is the US deterministic and ensemble forecast system. But in the drop-down menus, you can instead select to use the European ensemble, which is which is more skillful. So that's a forecasting tip. Choose the European ensemble for these tools.
Thank you. Well, since other folks are quiet, it seems that often ahead of cold fronts, we have these prefrontal jets, fast winds in the warm air just preceding the cold front that are transporting lots of moisture. But often the cold front just sweeps down across the coast so fast that it's not lingering. It's not pointing the fire hose at any one location for a long time. So from what I've seen, it's really the fact that this front stalls and lingers and points the fire hose at one location that seems to be the big issue there. But as you said in your talk, there are many other factors too.
Yeah, it's definitely, intensity and duration. Yeah, both important. But I think, for really catastrophic flooding, probably the duration is a necessary ingredient.
Rachel, go for it.
Hey, this is maybe a mean question. Any insights on how ENSO affects these and by its impact on jets? And was the fact that we had a lot of atmospheric rivers last year associated with La Nina, and the fact that we're having another La Nina this year, is that is there any info on that?
Let's see, okay. I don't know. I can't remember if I had any slides on that or not. Oh boy. I don't know. I haven't. I haven't. I think there have been studies on that, and I don't remember what they say.
Okay, no worries.
Yeah, I can.
My understanding is like, right, there might be, a link, but it's sort of similar to other rainfall things, that a lot of other things affect it, probably more so than ENSO is my vague understanding of that. But thanks.
Julia, go for it.
Thanks. Hi. Yeah, thank you so much for the talk. I was just curious. I think like a little while ago, I was sharing with our team already that there's this new study that was suggesting a new predictor for atmospheric rivers, and I think it's called the primary condensation rate. And just because you're like in the material, I was wondering if you know if that's used anywhere. I think they were also suggesting some adjustments to the pipe category scale. So
yeah, I think, was that Environment Canada thing maybe, or I can't remember.
I think so, yeah.
Yeah, there's also moisture convergence, which is another quantity I've seen used. I mean, again, I think I think both of those things can be useful tools for kind of diagnosing the events and looking at the different processes involved and stuff like that. But as far as forecasting, I think just looking at the precipitation itself is the best quantity to look at. But yeah, I haven't seen like this week at the conference, I haven't seen anybody using the primary condensation rate.
So, Greg, as you know, most of the numerical models smooth the terrain to enable numerical stability, but that smoothing essentially cuts off the top of the mountain ranges and fills in the valleys. And that would seem to reduce the amount of uplift and reduce the amount of precipitation. So what can we do to compensate for that fact that the mountains aren't high enough in the models?
Well, just off the top of my head, we could apply some sort of spectral filter and then increase the amplitude of topography. For those that don't know, this is already a project that WFRT is working on. Yeah, I mean, higher resolution models are one solution to that. Yeah, but again, the models obviously need to be tuned to whatever resolution of topography they have.
Do you have any other questions for Greg today?
I guess maybe I'll just jump in on that topic. And so there's a study some old colleagues of mine did on the topography around Panama. And sort of this same thing, that it's a very thin slice. And so in a global model, the average height ends up being pretty low. Then actually in reality, it's quite a high mountain range that does block a fair amount of transport. And so they just kind of went in and were like, well, instead of making this the average, let's make it the maximum. And so it is actually blocking this transport, and found that actually had quite a big impact and improvement on how the model simulated the circulation patterns around here. But I guess something that simple would probably mess up. I guess then you immediately mess up your temperature in the model if you've got the elevation wrong. But I just thought I would throw that out there as someone else sort of doing something, looking at the same problem but on a slightly different scale.
Yeah, that's definitely interesting. Yeah, but I suppose there could be, because there's like different drag parameters and stuff like that are in there to compensate for the smooth terrain, and so you want to make sure that you just make other corresponding adjustments.
Yeah. Hi, Greg. Sorry, Zane here. So on this topic of the topography being important, which I agree with very much, is I saw in your slides where you guys had a problem with where you over-predicted the rainfall coming from an atmospheric river. Was this situation inland behind the topography or not? So you had two cases.
About this,
yeah,
exactly.
exactly. Yeah.
So this one actually, sorry, we under-predicted the rainfall. The blue is the observed.
Right. Okay.
Yeah. So, these are on the generally the windward side of the coast range.
Right. Okay. Got it. I thought it was the other way around. This is why I was curious. Thanks.
Yeah, another thing to mention with atmospheric rivers kind of in general is that we've noticed that they're generally, I guess, less, the rain shadow effect is less pronounced compared to other events. When you have that stronger cross barrier flow, there tends to be more kind of spillover precipitation into the lee of mountain ranges.
All right. Well, if no one has any further comments or questions, I just want to thank you, Dr. West, for teaching us about atmospheric rivers today. This was a really interesting talk. Would you mind sharing your presentation on Slack with us? I know we were recording it, but would you also mind sharing the slides?
Yeah,
thank you.
Yeah.
Great.
Thanks for having me.
Yeah. If I guess if there are any further announcements, then that concludes today's atmospheric science seminar. So thank you, Dr. West, and thank you all for joining.